In this video, I will talk about why we add bias in neural network. We start with one simple example. Suppose we have data, a very small data, and there are two kinds of data we have over here. And suppose that there is a line that is always remains static. Suppose this is a line that passes through the origin, and this is the coordinate system. Now you can see that if we have this static line, then it is not classifying the data into the white and the another color. So what we needed over here, we needed a line, for example, a line like this, or maybe some kind of line like this that can classify the data. Maybe a line like this, right? So it means that we have to add something in the domain, so that one line can move and predict the classification. This is the motivation of studying the bias term. I will explain how this bias is added. But remember that there are other explanations as well. Sometimes it happens that the convergence becomes faster when we add bias into the neural network. So I'm going to discuss how bias affects the neural network. Okay, let me just start with a simple example over here. Suppose we have two inputs, input number 1 and input number 2. Suppose that from input x1, and remember there is only one output, this is output. Suppose that we have a link from input x1 to the output, and there is a weight w1. So what we do, we multiply x1 with w1. This is w1. Now for the second input, we also link that to the output. This is the output, and this is w2. So we have w2 over here. So what we do, we add these together, plus x2 w2. Since we have only two inputs and one output, this summation will be equal to E. The sum of these two expressions will give you E. But remember, there is no bias term added into the summation. So what we do, we add bias term over here. So in fact, you change the position of your line. This is not a line. This is in neural network, we don't have a line. We have some curve, tangent, hyperbolic, etc. This is just imaginary example. So we have a line that whose input has been moved towards right or towards left. It depends whether the bias is positive or negative, or positive bias is added or negative term is added. So we have added the bias term over here. So this will be equal to, the output will be equal to, in the summation form, that will be equal to E. But we know that in order to activate, whether a neuron is activated, this neuron is activated or not, how we decide that? We have to apply the activation function over here. Activation function will be applied over here. Okay, so when we apply the activation function, we get f of e, that will be equal to f of x1 w1 plus x2 w2 plus b. That's how we get the answer for one output. So we call that equal to A. So f of E will be equal to EA, and this is the activation function. Previously, we were working only on this expression, but now we have added a bias term, and you saw the motivation. We need to move our activation function. For example, if we have this activation function, if B is negative, the activation function will move towards right like this. If B is negative, the activation function will move towards the, if it is positive, it moves towards the negative side. We know that this happens from calculus. In calculus, if we have a function y is equal to f of x, and if we add anything in the input, x plus h, and h is greater than 0, if plus is added and h is positive, then the function will move towards the left. And if it is, for example, negative and h is greater than 0, so you are adding negative into the x, now the function will move towards the right. Okay, so here it also depends the bias where we want to move our activation function so that it can cover most of the data. So this was all about the bias term. Now we need a calculation that incorporates the bias term as well. So let me just write one input, where in input we have x1, one input, and another one is x2. So this is the input layer. This is input layer. Input layer. Then we have, in the middle, we have hidden layer. This is hidden layer. Then we have a output, a very simple network. This is output. Now we need to write this as a summation and as activation function. Suppose that we have a link from input to the first neuron in the hidden layer, then this is W1. And suppose the link from X2 to the hidden layer, the first neuron in hidden layer is W4. This is W4. Okay, so the answer with with summation and Bayes term will be equal to x1 multiplied with w1 plus x2 multiplied with w4 and the Bayes term plus b1. This will be equal to e1. This will be equal to e1. Okay, so we remove that. Now, since there are three neurons in hidden layer. Suppose we have one link from input x1 to the second neuron in the hidden layer, and we call that W2, and from x2 we have W5. This is W5. Then E2 will be equal to x1. From x1 to the second neuron, we have x1 W2 plus x2 W5 plus Bayes B2. So we have E1 for this neuron and E2 for this neuron. And the last one is, suppose we have link from x1 to third neuron in the hidden layer. That will be, for example, W3, and we have from x2 to third neuron in the hidden layer, and suppose we have the weights W6. So E3 will be equal to x1 W3 plus x2 W6 plus B3. That's what we have over here. So neat and clean, we write it like this. So these are the three neurons. The step is still incomplete since we did not apply the activation function. Let me just apply the activation function. So when activation function is applied on E1, we get f of E1. This will be equal to A1. Similarly, when the activation function is applied, let me just move this towards the right. This is one single neuron, and here A2 will be equal to f of E2, and for third neuron, after activation function, we have A3. Now, again, from this neuron, which acts as an input, there is an output. Suppose we have W7, which is a weight function. So for this, we have E4 and W7. This time the A1 acts as an input. The answer after activation function has been applied. We have A1 multiplied with W7 plus, then we have, for example, from second neuron in the hidden layer. That neuron acts as an input for this output, and we have W8 as a weight function. So A2 is W8 plus plus plus. Then we have a connection from third neuron to the output, and we call, for example, this as W9. So we add that A3 W9. That is the output. Okay. So we did not add the bystem over here. We need to add the bystem, which is B4, since we already called the bystem over here as B1, then we have B2, then we have B3, and this will be the B4. Now we apply the activation function to check whether the output is important. So this is FE4, and since this is output, this is the answer, we call it as Y hat. That's how the things work when we have added the bystem. So quickly, I write this as a mathematics in mathematics. So E1 will be equal to this term over here. This is E1. Then we have E2 over here. We want to write this as system of equations, E2. Then we have E3. This is E3. Okay, so that's what we have as a summation. Then after applying the activation function, we had over here A1 will be equal to f of E1, A2 that will be equal to f of E2, then we have A3 f of E3. And similarly, we can also write the output value, and the output value is written over here. I just copy that, maybe from here. So this is the output value plus B4 plus B4, and then we have, after applying the activation function, we have f of E4. That's how the things, there should be W9 as well plus B4. We have to apply the activation function later on. Now, how the forward propagation works in this whole scenario. I think you understood the bystem, how the bystem is added over here. The video is a bit longer, so I will talk about the forward propagation in the next video. Thank you for watching.